I figured I'd be here alone. Okay, we'll go ahead and get started. Can the people on Zoom see the slide and hear me okay?
Yes.
Thank you. So what we're going to do today is we're going to finish up chapter 13. And then on Thursday of this week, we'll have a quiz on chapter 13. So where we left off the other day was we were talking about these units of concentration, and we covered mass percentage, part per million, and part per billion. So what we'll do now is we'll pick up at mole fraction. So mole fraction is simply the ratio of the moles of a substance to the total number of moles in the solution. So with part per million and things like that, weight percent, it's usually solute over the total. In this case, it can be the solute or the solvent in terms of the mole component. It can be the solute or the solvent in terms of moles of component, and then that's divided by the total moles of all the components. So let's take a look at an example of this. So in this case, we're told that we have 36% HCl by mass, and we want to calculate the mole fraction of HCl in solution. So to do that, we would want to change our mass of HCl into moles. And remember, when we have a percentage like that, excuse me, when we have a percentage like that, we can assume that for the purpose of the calculation that that's 36 grams of HCl per 100 grams total. So in this case, to calculate the moles of HCl, we would have to find the molecular weight of HCl, and that's 36.5 grams. And so we would take our 36 grams of HCl times 1 mole of HCl per 36.5 grams of HCl. And that tells us that we have 0.99 moles of HCl. Well, we want to calculate that total number of moles that are present. So now we need to calculate how many moles of water are there. Well, if we said it's 36% by mass HCl, then that means the other 64 grams are water. So we would need to find the molecular weight of water, which is 18. And so we take our 64 grams of water times 1 mole of water per 18 grams of water, cancel out those grams, and we get 3.6 moles of water. Then to do that mole fraction, it would be moles of HCl divided by the total moles, which is moles of HCl and moles of water. So in the numerator, we'd have our 0.99 moles HCl, and then in the denominator, we'd have the 0.99 plus the 3.6 moles of water for a total of 4.6. And then if we do that math, we get 0.22 as our mole fraction. So we just as easily could have calculated the mole fraction for water. And in that case, it would be the 3.6 in the numerator. And then we would get a different answer for that. So with mole fraction, make sure you note which compound that you're being asked to calculate for. The next two we'll talk about are molarity and molality. So molarity, which is the capital M, that's probably one of the most common ways to express solution concentrations. And we talked about this last semester, and you've been using molarity calculations all along, so hopefully this looks familiar. And that's moles of solute divided by liters of solution. And so moles per liter. Molality is slightly different. It's moles of solute, just like molarity, but it's per kilograms of solvent. There's a few specific applications where people use molality. Most of the time, though, you're using molarity. So the other thing is molality is expressed by a small m. So you have to take note, is it a big M or is it a small m? And just to confuse you a little more, you often are talking about millimolar, and that's a small m next to a big M. So let's take a look at a molarity example just to refresh your memory. In this case, we're saying that we have 0.68 grams of potassium phosphate, and we're making that solution up into a 1 liter volumetric flask. One thing about molar solutions is you almost always make them up in volumetric flasks. That way you know what that total volume is. So we would have our 0.68 grams of potassium phosphate. We would multiply that by 1 mole per 136 grams. We were told that that 136 grams per mole was the molecular weight for the potassium phosphate. It's per 1 liter of our 1 liter volumetric flask. So if we go ahead and do that, we get 0.0050 molar potassium phosphate. And then next we have what it would be in millimolar. That's what I was mentioning just a moment ago. Millimolar, you have the small m next to the capital M. And we remember that milli is 1,000. So we would slide our decimal place over 3 places to the right to switch from molar to millimolar. And in this case, that results in 5.0 millimolar potassium phosphate. So hopefully nothing on this slide is new to you, because we've been doing these molar calculations for some time now, but that's just a quick review of it. So when we think about molarity and molality, if water is the solvent and the solutions are dilute, the molarity and the molality are usually pretty much the same. Molality, because mass doesn't change, it doesn't vary with temperature. Molarity, in theory, can vary with temperature, because as temperatures change, volumes change. But really, unless you're going to kind of extreme temperatures or aggressive temperatures, it really doesn't change that much. We've been using dimensional analysis for quite some time. So you need to do dimensional analysis to convert from molality to molarity or back and forth, because in that case, you need to have the density of the solution to be able to do that conversion. Like I said, if it's water and it's dilute, it usually works out to be about the same. But when you start getting to some other solvents or more concentrated solutions, then it can make a difference. Once again, the dimensional analysis, I think we've been doing that pretty routinely in all the problems that we solve. So that shouldn't be anything new to anyone, hopefully. So there are some homework problems. I'd like to go over a few of these, just so everyone's kind of on the same page with this. So let me pull these up. So I know that there's been a few people who have just kind of come in a little bit late. I know it's difficult with the weather out there, so glad you could make it. I do want to just remind everyone again that we do have a quiz on chapter 13 on this Thursday. So as I said at the beginning, we'll finish up this chapter today, and then on Thursday, we'll have a quiz on this chapter. Okay, so in 13.4.1, we're told we have 14.6 grams of methanol and 184 grams of water. And then we want to do some calculations off of that. So the first thing that I did was I went ahead and found my molecular weights for methanol and water. So molecular weight of methanol is 32, for water it's 18. And then in part A, we're being asked to calculate a mole fraction for the methanol. And so remember, mole fraction is the moles of the analyte, the solute. In this case, that's the methanol, divided by the total moles. So in the numerator, we took our 14.6 grams, divided it by 32 grams, which is the molecular weight for methanol, to give us moles of methanol in the numerator. In the denominator, we have that same expression for moles of methanol, But then we need to calculate the moles of water. And so we were told there were 184 grams of water. And so we convert that 184 grams using the molecular weight into moles. So we have moles of methanol in the numerator, moles of methanol, plus moles of water in the denominator. We get then 0.456 divided by 10.68, and that gives us a value of 0.0427. So key there is just remembering mole fraction is moles of whatever analyte you're looking for. In this case, it was the methanol divided by the total moles. In part B, we're doing a weight percent. And so weight percent, grams of the methanol divided by total grams. So grams of methanol, 14.6 grams. Total grams would be that 14.6 plus the 184 grams that are from the water. Since it's a percentage, we express that by multiplying that ratio by 100, and we get 7.35%. In C, we want to calculate the molality, so that's the small m. And so we need to remember that molality is moles of solute divided by kilograms of solvent. And so in that case, once again, as we've done before, we're going to convert that 14.6 grams of methanol into moles using the molecular weight. And then the denominator, we have 184 grams, and we want to change that to kilograms, because remember, it's moles per kilogram of solvent. So we just simply can do the conversion of 1 kilogram is equal to 10 to the third grams. If we go ahead and do that math, we get 2.48 grams moles per kilogram. So any questions about those calculations? Let's look at 14.43. In that one, we're told we have 0.540 grams of magnesium nitrate and 250 mils of solution. So as I was saying previously, I always like to calculate the molecular weight first. And so go ahead and calculate the molecular weight for the magnesium nitrate, and you get 148.3 grams per mole. So then once you have that value, then you can go and start doing some of these calculations that they want. And so the first one is molarity. Calculate the molarity of this solution. Molarity, definition of that is moles of solute per liters of solution. We had 0.540 grams. Multiply that by 1 mole over the 148.3 grams for the molecular weight. That gets our numerator into moles of magnesium nitrate. In the denominator, we have 250 mils. We want to convert that into liters, remembering that milli is 10 to the third. And so if we go ahead and do all that math correctly, we get 0.0146 moles per liter. If we wanted to change it into millimolar, we would simply slide that decimal place 3 spots to the right, and we'd get 14.6 millimolar. In part B, we're told we have 22.4 grams of LiClO4.3H2O. So here we've got a lot of stuff going on there and it's in 125 mils of solution. So here we've got a lot of stuff going on when we calculate our molecular weight. So the lithium, the chlorine, those are pretty easy. The hydrogen, we need to remember that it's 3 water molecules. There's 2 hydrogens in each of those, so we'd have 6 hydrogens there. 3 water molecules, 2 hydrogens in each. The other one we have to be a little careful about is the oxygen. We have 2 sources of oxygen here. We have the LiClO4, so we have 4 oxygens coming from there. But then we also have the 3 water molecules, and we have 3 oxygens coming from there. So we have a total of 7 oxygens. So here we have to make sure that our oxygen atomic weight of 16, that we multiply it by 7 to account for all those. I know sometimes people get a little confused and they forget to add the oxygens from the water, or they just add one of them. Make sure you have all 3 from the water, and in this case, the 4 from the other part of the compound. So if you do all that stuff correctly, then you get a molecular weight of 160.44. And so that's what we would need. So now to calculate our molarity of the solution, we would take our 22.4 grams, do dimensional analysis, 1 mole per 160.44 grams. That converts our numerator into moles. We had 125 mils of solution. Once again, to change the mils into liters, we can just slide the decimal over 3 places, and that's 0.125 liters. And then if we do that math, we get 1.12 molar. Any questions about these molarity calculations? So in these first couple of homework problems, we've done calculations of most everything. We've done the molarity, we did molality, we did weight percent. The only ones I think we didn't do were the part per million or the part per billion. So remember, part per million is 10 to the 6th, part per billion is 10 to the 9th. So those types of problems are done the same way as that weight percent problem was. The only difference is in weight percent, after we got our ratio, we multiplied by 100, versus if it was ppm, it would be times 10 to the 6th instead of 100. If it was ppb, it would be 10 to the 9th times 100. So don't let the ppm, ppb thing confuse you. It's the same type of calculation as the weight percent. It's just what you're expressing it in and doing that last calculation. Okay, one more part here. This should bring back memories of Gen Chem lab last semester. 25 mils of a 3.5 molar nitric acid solutions diluted to 0.25 liters. What is the molarity of the new solution? This was our old friend M1V1 was M2V2. So if our first solution, 0.0250 liters, remember we're converting it to liters. And then 3.5 molar, our new solution is what we're trying to solve for, M2, and then V2 in that case is 0.250 liters. So the key here is you can either have both those volumes in liters or both in milliliters. It'll work either way. What you can't do is have one in mils and one in liters, then you'll get the wrong answer. So in this case, I chose to convert them both into liters. And then if I do that and then solve for M2, I get 0.350 molar for that new concentration. So once again, this should look familiar, hopefully, because last semester we had this in the lab, we had it in the class, you saw it quite a bit. Any questions about that one? Okay. Let's look at 13.47 and go through some of this. So in this case, we're told we have 571.6 grams of sulfuric acid per liter. and we're given the density of 1.329 grams per centimeter cubed. What else is centimeter cubed represented as? It's represented as mils, right? So don't let the centimeter cubed thing throw you off. Grams per centimeter cubed is the same as grams per mil. So in the first one, we want to have a weight percent. And so here, we're told we have the 571.6 grams of sulfuric acid, and we're told we have 1 liter of solution. So we can change that liters into mils. That's 10 to the third mils equals 1 liter. And then that's where our density comes into play, okay? Since it's a weight percent, we needed mass in the numerator, then mass in the denominator. We started out with mass per volume. So we had to change that volume term in the denominator into a mass term. And we can do that because we were given the density. That's this 1.329 grams per mil. We needed to get our liters into mils. And then once we did that, we can use the density value. That'll give us that ratio of the mass of sulfuric to the total, and then times 100 to change it into a percentage. Okay, in part B, we want to calculate a mole fraction. So here, since we're going to be working in moles, we're going to need to know the molecular weight for sulfuric acid and for water. And so if you calculate the sulfuric acid one, you get 98.065 grams per mole. Water is 18 grams per mole. And so now what we can do is it's a mole fraction. So what do we want? We want moles of our solute divided by the moles of our solute plus the moles of our solvent. And so here, in the numerator, we use that molecular weight that we calculated for sulfuric acid to find the number of moles of H2SO4. In the denominator, it gets a little bit tricky because one of the things we had to do is figure out how many moles of water we had. Moles of sulfuric is easy, that's what we have in the numerator, but this moles of water is a little bit trickier. So one of the things we had to do is figure out how many grams of water that we had present, because we weren't told that. We were told some other information, but not that. So to get our moles of water, what we had to do was we had moles we had the grams of the sulfuric acid that we had to find out. And then we had to subtract from that, we had the total grams, and then we had to subtract the grams of the sulfuric acid. So we were given a density up there of 1.329. So we know that if we have a liter, if we assume we have a liter, then it's 1329 is the total grams. We subtract our 571.6, and that tells us we have 757.4 grams of water. So that's where we got the 757.4 grams of water from. So by assuming that 1 liter of solution, we're able to calculate grams of water, and then using the molecular weight, we can get to moles of water there in the denominator. So then we have the moles of the sulfuric acid, we have the moles of the water, and then that's our denominator. And then if we do that math, we get our mole fraction of sulfuric acid, 0.122. Okay. Any questions on that? Any of those? Then we wanted to calculate the molality. And we know once again that molality is moles per kilogram of solvent. So here in the numerator, we calculate our moles of H2SO4 using that molecular weight. And then in the denominator, we had calculated the number of grams of water that we had in that last part of the problem. And so then we just need to convert that to kilograms. And then we do the math and we get 7.70 moles per kilogram of solid. And then the last one is calculate the molarity. And so it's a 1 liter solution, as we've been told. And so once again, we calculate moles of sulfuric acid in the numerator, and then it's per liter. So then that comes out to be 5.829 molar. So here you see that 5 molar solution is fairly concentrated. And so you see, we do see a difference between molality up on top. So molality for the solution is 7.7, molarity is 5.8. So we do see a little bit of a difference there in concentration when we express it as molarity versus molality. If it was a much more dilute solution, you wouldn't see as big a difference. Okay, so that's the end of those calculations. I would say make sure you're comfortable doing all those kind of calculations. I would be shocked if there aren't some of those on the quiz on Thursday. I think if you just remember the definitions of the different ways to express concentration, you'll be fine. After that, it's just lining up your units and making sure the units are correct. Make sure that you take your time when you're calculating the molecular weight so you don't mess that up. But really, it's very similar to a lot of the calculations we've been doing in the class for some time now, where it's that dimensional analysis stuff that we talked about in the very beginning, and it's just a continuation of that. So if there aren't any questions about that stuff, I'm going to move on to colligative properties. So the fact that we had some snow today and you see people putting salt out ties in well to colligative properties, because one of the colligative properties is freezing point depression. And so what is a colligative property? Colligative property is something that depends only on the quantity, not the identity of the solute particles. And so the 4 main colligative properties that people tend to talk about are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. And I would say, you know, vapor pressure lowering, yeah, we kind of talk about that, but boiling point elevation, people do that almost every time when they cook and make spaghetti. You ever notice, like on spaghetti, it says add salt? Well, one of the reasons people will add salt to boiling water is then you get boiling point elevation. That's the idea behind that. And freezing point depression, well, that's why people are putting salt out. The salt will dissociate, so then you have 2 particles, 2 quantity, 2 pieces, however you want to think of it. And what that does is it causes freezing point depression. And so instead of the water freezing at 0 degrees C or 32 F, it pushes down that freezing point lower, and that's why it looks like it's melting. It's changed, you've changed the freezing point of the water by adding that salt. So like I said, that's one one positive thing to the bad weather this morning is that it gives us an example of colligative properties in use. The last one, osmotic pressure. We have an example later in the slides today of osmotic pressure that has to do with blood and cells and things like that. The other one that is a little more relevant for me personally is pickles. So I really like pickles, and so pickles, that whole process is when you pickle stuff, it's not the salt moving into the pickle, it's the water moving out of the pickle. And so that's an example of osmotic type of pressure. So colligative properties are kind of fun, I think, because you see them a lot in your kind of everyday life and you may not even realize it. So I bet when you got up this morning, you didn't think you were going to be talking about pickles and melting snow, but here we are. Okay, so vapor pressure. Remember we talked about vapor pressure a little while ago, and that is, if we look over here at these diagrams on the bottom of the slide, vapor pressure is that equilibrium between things that are in solution and then things that are volatilizing. And so you have, remember we talked about interactions also in solutions. We have the solute-solute interactions, we have the solvent-solvent interactions, and then we have the solute-solvent interactions. And so as you add more non-volatile particles into it, okay? So in this example, we're going to say that the solute particles are non-volatile and the solvent has more volatility than that. So as you add more of those particles in, you get more interaction between the solute and the solvent. And so that makes it harder for that volatile solvent to then kind of break away from the pack, so to speak, and go into the atmosphere. And so what that does is it slows down that rate of evaporation, and then it'll eventually re-equilibrate, but the result is you have fewer of those volatile particles in the atmosphere above the solution. And as a result of that, the vapor pressure of that mixture will be less than what the vapor pressure of the solvent by itself would be. So it's kind of neat, I think, because we've spent a lot of time talking about these intermolecular interactions and talked about how for solutions, once again, you have solute-solute, you have solvent-solvent interactions, and then you have solute-solvent interactions. And it's showing us that these interactions, by kind of disturbing what they normally would do, we actually change a property of something like vapor pressure. So if you had something that was pretty volatile and you wanted to reduce that volatility somewhat, you could put in some non-volatile particles, some non-volatile solute into it, and it would help reduce this equilibrium, and you'd have less in the vapor phase. There's something called Raoult's law, which helps explain this. And what this law tells us is that the vapor pressure of a volatile solvent is the product of the mole fraction of the solvent times the vapor pressure of the pure solvent. So in other words, we have a solvent. Say, for instance, it was, I don't know, let's say it was methanol. We had methanol, and we could calculate or look up in a table what the vapor pressure of that is. Then, if we added a non-volatile solute into it, some particles into it, then we could calculate what that mole fraction is for the solvent, for the methanol, and then that would tell us what the vapor pressure of that new solution would be, okay? when we have mixtures of solutions, we assume that each substance in there will follow Raoult's law while they're in the mixture. So in other words, if you had a mixed solvent system where a couple things in there were volatile, plus you had some non-volatile solutes in there, you could calculate out what the vapor pressure would be based on them all behaving ideally. So boiling point elevation. Since the vapor pressures are lowered for solutions, remember that's what we talked about here. We said we're lowering the vapor pressure. Since the vapor pressures are lowered for solutions, it requires a higher temperature to reach atmospheric pressure. That's why you get the boiling point elevated, okay? It goes back to that first colligative property that we talked about. Vapor pressure is lowered in the solution, so it requires more energy, more temperature to get it up to the point of where it's boiling. You can kind of explain this through these phase diagrams that we talked about previously, but really the key thing is just the statement is the colligative properties result in that lower vapor pressure that we talked about, since it then requires a higher temperature to reach the atmospheric pressure. Okay, I have to put more energy. So boiling point is raised. So once again, going back to the cooking spaghetti thing is, you put the salt in, the salt dissociates, you get a lot of particles in there, the sodium and chloride atoms, and then now boiling point is going to be hotter, going to be higher. Similar thing with freezing point. And this goes back to the phase diagram, which you can take a look at. But with freezing point depression, the freezing point is lowered as the boiling point is raised. And so once again, the result is we spread the salt out on the snow, the ice. It lowers the freezing point, depresses the freezing point. And so now if it's 0 degrees C out, it starts to melt because the freezing point no longer is at 0, it's at minus whatever. You can do some calculations around both of these, around boiling point elevation and freezing point depression. And the change in temperature, so you can go and calculate, if you have some of this information, what that new freezing point or boiling point is. You can do a calculation to determine what that is. And this is one of the times that you do use molality, okay? So there's something called the Van Hoff factor, and that's the number of particles a substance becomes when it dissolves. So what do we mean by that? If I take sugar and dissolve it, I still have one particle because sugar doesn't ionize, it doesn't dissociate, it doesn't do anything like that. So one sugar molecule in water results in one sugar molecule in water. If I take salt, sodium chloride, and dissolve it in water, that's going to dissociate. We'd have sodium plus ions and chloride minus ions. So in that case, I'd have one piece, so to speak, then becomes two. And so that's what in these equations, the I value is that Van Hoff factor, and that's what that represents. The number of fragments that a solute breaks up into. So if it's a non-electrolyte like the sugar, in other words, it doesn't dissociate into the ions, then it's just, the number is just 1. If it does dissociate, so if it is an electrolyte, it's going to at least be 2, depending upon the stoichiometry of the molecule, it could be more. In the sodium chloride example, like I said, it would be 2, 1 sodium ion, 1 chloride ion. But it could be more depending upon what the ion is made of, what that stoichiometry is. So in our formula, we get that change in temperature, delta TB or delta TF, depending if we're looking at boiling points or freezing points. And so the formulas are pretty much the same. It's that Van Hoff factor, which is dependent upon how the solute behaves in the solution. Is it an electrolyte or not? There is this K value, which is a molal boiling point or freezing point, boiling point elevation or freezing point depression constant. So those are values that you would have to be given or look up in a table. And so then you would plug that value in, and then finally we have small m here, which as we learned earlier is molality. And that's where it would be moles of solute divided by kilograms of solvent. So like I said, this is one of the times we do need to use molality. So in order to solve a problem associated with this, you'd have to be given the constant. You'd have to be able to calculate molality of the solution you're dealing with. And remember, molality again is moles of solute divided by kilograms of solvent. And then you have to think of what is that solute that you're putting in. That's this Van Hoff factor that's represented by I. And so you'd have to think about, is it an electrolyte or not? If it's an electrolyte, then it's going to break up into pieces, so to speak, ions, however you want to think of it. And then that would be 2 or 3 or 4 or whatever. If it's not an electrolyte, once again, use that example of sugar, then it would just be the number 1. So this is a way where you could go ahead and calculate out what that delta T is. So in other words, what's that boiling point elevation or freezing point depression is, if you have some of this information. Okay, let's talk about osmosis a little bit. So there are some things that form semi-permeable membranes. And what that means is that small molecules can pass through the membrane and bigger ones that physically can't fit through there can't go. They're just stuck. Think of it as kind of like a fence. And there's some holes in the fence, and if you're small enough, you can get through. If you're not small enough, you can't get through. That's what we're talking about in essence with semi-permeable membranes. So what usually this means is that it's the solvent molecules that are moving. And like I said, water is a real common one. That's the pickle example. That's the blood example we'll see here in a little bit. And so what happens is the solvent molecules move from low to high concentration across that membrane. Because really what they're trying to do, they're trying to get things equal. They're trying to get equilibrium established. And so this solvent moving across the membrane from low to high concentration is called osmosis. And then the applied pressure to stop it is called osmotic pressure. So remember, it's not the solute molecules that are moving. So you have low concentration, a real dilute stuff, and then you have a higher concentration. So you have more solute on one side than the other. The solute doesn't move across the membrane. It's the solvent that moves. And so in other words, the solvent's moving from the low to high to decrease that concentration of the higher concentration side of the membrane, okay? And like I said, talking about the pickle example again, You think of how you make pickles. You have the cucumber. It's got a lot of water in it. You put it in some type of brine solution. There's always a lot of salt or something like that, but there's a lot of particles, think of it as. Remember we talked about the Van Hoff. Got a lot of those strong electrolytes in there that are dissociating. And so now you've got a higher concentrated solution on the outside of the pickle. So the water from the pickle moves out to try and dilute that out around it. So it's not the salt moving in, it's the water moving out. And then the stuff in the cucumber gets concentrated more because it's lost some of that water. So you can calculate osmotic pressure. And here we have a formula for that. Once again, we have our Van Hoff factor, I. That's the same as what we talked about on that freezing point and boiling point changes. M, now this is capital M. So that's molarity, moles per liter. R is our old friend, the gas constant from the ideal gas law. And if you recall, that is 0.821 liters atmospheres divided by moles Kelvin. And you think about it, at first it seems a little weird that we're using a gas law type of constant, but we're talking about pressure. So pressure, we think gas. And then finally, T is the temperature in Kelvin. So once again, we can calculate osmotic pressure by using the Van Hoff factor, which is the small I, molarity, which is the capital M, R, which is the gas constant, 0.0821 liters atmosphere divided by moles Kelvin, and then times T, the temperature. And we need to make sure we express that temperature in Kelvin. So if two solutions separated by semi-permeable membrane have the same osmotic pressure, then nothing happens. So no osmosis will occur. So when we talk about solutions and osmosis, there's a few terms that we need to be familiar with. One is the term isotonic solution. And so with isotonic solutions, you have the same osmotic pressure. And what this means is basically it's at equilibrium. So the solvent is passing across the membrane back and forth at the same rate both ways. So there's no net change in any concentrations. It's kind of like when we talked about vapor pressure in the gases. You're at equilibrium, so it's not just sitting there, but it's going back and forth at the same rate, so there's no net change. A hypotonic solution means you have lower osmotic pressure. So that means the solvent will leave the solution at a greater rate than it enters with. So in other words, now you're out of equilibrium and you're moving in one direction. Hypertonic means you have higher osmotic pressure, and so the solvent will enter the solution at a higher rate than it leaves it. So isotonic, hypotonic, and hypertonic are the ways we explain whether something's in equilibrium or if the solvent's moving out of or into our solution that we have. So this applies to blood cells, to red blood cells. And so let's take a look at this a little bit. So red blood cells have semi-permeable membranes. If stored in a hypertonic solution, they will shrivel as water leaves the cell. Remember, we said hypertonic was what? Hypertonic, higher osmotic pressure, solvent will enter the solution at a higher rate than it leaves with. So for this case, hypertonic, water will leave the cell, and it's leaving faster than coming back in. And so they'll shrivel up, and this is called crenation. If you store it in a hypotonic solution, then the water will keep going into the blood cell and keep going, and they'll eventually burst. And that's called hemolysis. So IV solutions, so intravenous solutions, they must be isotonic, okay? Remember we said what isotonic was? Same osmotic pressure, solvent passes across the membrane both ways at the same rate. We certainly don't want either the blood cells to shrivel up or to burst. That would be bad, of course. And so this is why you'll always see a lot of times when certain drugs or whatever are administered, they're administered in an IV solution, and it's to maintain this isotonic type of situation. Because if you had the drug and you're infusing it for a long period of time, and it got this out of whack, then you could have one of these problems. But by diluting it in that IV bag, which is usually some type of isotonic solution, then it mitigates the problems you would have with whatever the actual drug is that you want in there. So down here on the bottom are just some drawings of blood cell. The first one is the isotonic, everything is fine. We see the arrows coming in and out at about the same rate. We then see our second example of where it'll shrivel up because we have too high of a concentration outside the blood cell. And so the solvent, in this case, the water, will leave the blood cell to try and get equilibrium established. Well, if it's much too high concentrate solute outside the cell, then it's going to just shrivel up because it's going to have the water keep going to try and get things balanced out. And then the third example just once again reinforces that if the solute concentration is higher inside of the cell and the solution around it is lower solute concentration, then that water is going to move from the solution outside the cell into the cell to try and balance things out. And the result is this blood cell takes on more and more water, and eventually it can't handle it anymore and it can burst. So like I said, you can think about the osmosis stuff in terms of the blood cells. You can think of it in terms of the pickle. I personally prefer the pickle one myself, but I know a lot of you are biology majors, so you might appreciate the blood one more so. So any questions on those colligative properties? Okay, so like I said, I kind of like the colligative properties. They're real, what I think, real practical type stuff that you see all the time and maybe didn't quite understand what was going on. And so it's a nice, I think it's a nice example of chemistry stuff that you experience on a day-to-day basis. So now I want to talk about something called a colloid. And colloids are real big in liquid formulations. And by liquid formulations, think of it as any type of product that you use that's in liquid form. So, you know, this morning you may have washed your hair with some shampoo, or you may have used body wash or something like that, or face wash. All of those, I guarantee you, have colloid type applications to it. And so when we're talking about it, colloids, we're talking about suspensions of particles larger than the individual ions or molecules. So in other words, you really don't see it, at least you shouldn't see it if the product was made properly, but there's really, if you looked at it closely, under a microscope or scattered light or something like that, that there's actually clumps of molecules floating in there. Probably the most common or most famous colloid system is cow's milk. So cow's milk, you know, you can let it sit there forever and it doesn't settle out. Now, I'm not talking about spoiling, that's a different process, but I'm just saying that colloid, the cow's milk is actually a big colloid system. So you've got all these particles that are suspended in there, but they're suspended so well that you don't see them and you don't realize that's the case. And so the colloids are the dividing line between solutions and suspensions. And so this gets into just really some semantics. And so solutions are considered where everything is fully dissolved. And so in other words, if you took a laser light and shined it into a solution, the light would just simply pass through, except where you'd have energy absorbance, but there'd be no physical scattering of that light. Suspensions are where you literally have little particles and you probably can see them, okay? And once again, if you shine light in, you would get scatter of that light because it hits like little pieces and the light scatters. Colloid is in between those two. And colloid is, the reality is there are things that are clumped together, but you really shouldn't be able to see them. But you can, there are ways to detect it. Some of the colloid types, a lot of aerosol products are colloids. Foams are a big one. There's something called emulsions. Milk is considered an emulsion. Marshmallow is another one that's a solid foam. Some different examples here of that. But what colloid's big purpose is, okay, let me just mention the Tyndall effect before I get to that. The Tyndall effect tells us that colloidal suspensions scatter rays of light and solutions do not. So this is one way you can tell if you have a colloidal suspension or if it's just a solution. And so down here, might be a little difficult to see on the photo, but the one on the right, you see it looks a little different than the one on the left. The one on the right looks a little different because as this light is shined through, you get that scatter. So when people are trying to figure out what type of material it is in terms of a colloid suspension or some of these others, it's almost always by shining light in and seeing how the light scatters. But the thing I wanted to point out is that colloids typically have a polar end, which we say is hydrophilic, which means water-loving, and a non-polar end, which we call hydrophobic or water-fearing. And so what this does is you have these big molecules and you have a polar side, a hydrophilic side, and you have a non-polar portion, hydrophobic. And what this does is colloids are really good at solubilizing things that normally wouldn't be soluble. So remember we talked about like dissolves like? We said that polar things like to hang out with polar things, non-polar like to hang out with non-polar. Well, a lot of times when you're making a product, you have some things in there that are polar and some that are non-polar, but they need to be in there for a particular reason. You can't get rid of one or the other. Well, what do you do then? Well, you look for compounds that kind of bridge the two together. And that's where these colloids come into play. And so if you have a polar end, well, that's going to be more oriented towards water and other polar type molecules. And then the non-polar end will be oriented around the non-polar type compounds. And since they're usually pretty big compounds, you have some distance and space there, which allows all that to kind of stay together. You can almost think of it as if you've got two people arguing And you need someone who's a peacemaker in the middle to kind of get them both, because the two can't really talk to each other. They're too upset. But this molecule in between can talk to each of them kind of at the same time and smooth things over so everything stays together. So colloids are really important in serving as like these bridging molecules. You know, it's interesting because if you watch enough TV and see the commercials, especially the shampoo commercials, they'll always say we don't have a certain compound or something like that. Well, a lot of times, you know, and people say, well, why is that in there? A lot of times the compound is in there to serve as a colloid, to kind of get the different components that you really do need in there to behave together so you don't have things separating out, okay? So when they make those statements, I guarantee you, they may not be using that particular compound, but they're using one similar, because you need that physical polar, non-polar type of ends to make things balance out and stay stable. Another thing you can do is if you have a colloid that's just hydrophobic, a lot of times you can absorb ions onto it. And once again, what that does is it allows it to interact with the water. So there's some tricks you can play there too. The key thing about this colloid stuff in general is whether it's a design colloid to have a polar, non-polar end, or have one that can have some interaction with ions. What you're trying to do, once again, is have a molecule that has dual properties in order to bridge some of the components that are in your mixture. You see colloids in biological systems, and that comes into when we talk about emulsification of fats and oils in aqueous solutions. When we talk about emulsifying something, we're talking about something that normally doesn't dissolve, getting it to dissolve. And this goes back to that like dissolves like thing that we mentioned early on. And one of the things I'm hoping you remember is if we look at, in this case, we've got an oil droplet here, okay? The oil droplets are almost always nonpolar. And then we see stearate, okay? And we see with stearate, we have a hydrophilic end, that's the red stuff over on the right. And then we have a long chain, long alkane chain here, that's the white and the black atoms on the left. That's a real non-polar end. And so what we see is if we had some oil and water, then this non-polar end will interact with the oil droplet. The polar end will interact with the water, then it helps us solubilize that oil. And so once again, that's the purpose of the colloid, whether it's a biological system or some other system, is to do this bridging just to help us kind of violate that like dissolves like rule. The rule's still valid, but there are just some tricks you can do by taking advantage of these longer molecules, these bigger molecules that have a hydrophobic, so non-polar end, and a hydrophilic polar end. So to me, that's pretty neat. I like that. Okay, so there is some homework associated with this. Before I start on going through a couple of those problems, any questions about any of this stuff that we talked about with colligative properties and colloids and stuff like that? Okay, let's take a look at a couple of these homework problems. First one, 13.7.5. So in 13.7.5, we're told we add some ethylene glycol is added to 1 kilogram of water to reduce the freezing point to minus 5 degrees. How much did we add? So we have our formula, which we talked about before, which tells us that we can calculate out what that change from the regular freezing point or boiling point of something is. And we need to think about what the solute is in terms of electrolyte. We need to choose the right constant for freezing or boiling. And then we need to have molality. So for ethylene glycol, I'm going to go ahead and calculate my molecular weight. And if I do that, I get a value of 62. So now I have that, so I can be able to convert something into moles if I need to. And then let's think of ethylene glycol. So first of all, does anyone know where ethylene glycol is used pretty commonly? It's usually in your antifreeze in your car. And so ethylene glycol, though, if we look at that compound, the way the molecular formula is written, do we think that's an electrolyte or not? It's not. It's not going to dissociate into anything. And the reason why we know this is, see how we have C2H6O2? If this was going to dissociate, we wouldn't have H6 there. We'd have H5, and then we would have OH written on the end. For something to, when you write those molecular formulas like that, if it's going to dissociate, you got to pull one of those hydrogens out and have it on the oxygen. It can't be stuck in there between the carbon and the oxygen. So that's how we know this doesn't dissociate. So that means our constant, our Van Hoff constant, I, that value is 1, because it's not good, it's not a strong electrolyte. This 1.86 degrees C for molal, that's out of the table. We would be given that when we look it up in the table. That's the constant. And then we were told we had a 5-degree temperature change, -5 there. So now we need to just solve for molality, the small m. We go ahead and do that calculation. We get 2.69 molal. We know that that is equal to 2.69 moles per kilogram of water, right? By definition, molality is moles of solute per kilogram of solvent. If we want to then calculate out, as we were told, we're looking at 1 kilogram of water up in the beginning. And so if we want to find out how many grams of water grams of the ethylene glycol that represents, we can take 2.69 moles, multiply it by 62 grams, which was the molecular weight, divided by 1 mole, and we get a value of 167 grams of ethylene glycol. So if we had 1 kilogram of water, we would have to add 167 grams of ethylene glycol to change that freezing point from 0 degrees to -5 degrees. Okay, so once again, the key things we had to know, is this a strong electrolyte or not? We will substitute in for I, it wasn't, so we put 1 in there. We needed to remember that molality is moles per kilogram, and we needed to calculate a molecular weight there. Okay, the next one, we're told we have 44.2 milligrams of aspirin in 0.358 liters of water. And we want to do an osmotic pressure calculation. So first thing I'm going to do, I'm going to calculate the molecular weight of aspirin. So I have my molecular formula up there. I take that information, calculate the molecular weight, which comes out to 180 grams per mole. I know I'm going to be using that osmotic pressure formula, and I know that my temperature has to be in Kelvin. So I'm going to take my 25 degrees C and convert that to Kelvin. So that's 298. Remember, you had 273 to the degree C. So I'm kind of lining stuff up. I'm gonna need, excuse me, I'm gonna need a molarity. So I have 0.3, I have my 4.42, so 44.2 milligrams of aspirin. I know that I need that in grams to convert it to moles. So it's 44.2 times 10 to the minus third grams. Remember, milligram is 10 to the minus 3 grams. Divide that by 180, my molecular weight. So now I have moles in the numerator. I was told that I have 0.358 liters of water that I put it in. And so this, I have a value of 6.86 times 10 to the minus 4 molar solution, because that's moles per liter. I don't worry about that 44.2 milligrams of aspirin affecting this total volume here. That's a tiny amount of aspirin put into a bigger amount of water. So now I've got everything set up and I can plug things into my formula. So I need to determine that. I need to think of aspirin. Once again, thinking of how aspirin is written, since I don't have that hydrogen atom kind of hanging out on the end, I'm going to assume that it doesn't dissociate into anything. It's not a strong electrolyte. So I'm going to say 1 for that. I have my molarity, which I calculated up here, the 6.86 times 10 to the minus 4th. And then I have my ideal gas law constant, my old friend, 0.0821, and that's liters, atmospheres, moles, Kelvin. So what I need to have is, remember, my units are going to cancel out. This is the molarity, is moles per liter. That'll cancel out the liters and moles here. My temperature, remember I converted that to Kelvin, 298 K, so that cancels out the Kelvin unit, and now I'm left with units of atmosphere. That's great, because I'm talking pressure. I want some type of pressure unit. And so now I solve that, and I have a value in atmospheres. Okay, now, the last one we have is, which is the best emulsifying agent? And so here's our choices. CH3COOH, CH3CH2CH2 COOH, CH3, then 11 CH2s, then COOH. Then we have CH3, CH2, 11 of those, and then COONA. Okay, which one? So if we said we wanted an emulsifying agent, what did we say? We said for an emulsifying agent, we'd like it to have a polar end, a hydrophilic end, and a non-polar end, a hydrophobic end. So then we can have one side of the molecule that solubilizes the polar stuff and one side that solubilizes the non-polar stuff. We'd also like the ends to kind of be away from each other, right? So that they don't kind of conflict. So when I look at this stuff, so the COOH, that's called a carboxyl group. And carboxyl groups, depending on the pH, will lose that hydrogen atom, okay? We're not told anything about pH here, so we can't make any assumptions about what that carboxyl group is going to do. So we look at the first one, second one, third one, fourth one. They all might work because we've got a polar end and a non-polar end. But the first two, that non-polar end isn't real big. So I'm gonna say those probably aren't the best choice. Well, then I get down to these last two. The non-polar ends are exactly the same, a CH3 and then 11 CH2s. And then I have this carboxyl group, COOH, and then I have COONA. So the difference here is the one with the sodium has lost that proton. So now I have a carbon, and the way this would look is, and you don't need to know this, but the way this would look is a double bonded oxygen to the carbon, a single bonded oxygen to the carbon. That single bonded oxygen would have a negative charge on it, and then the sodium ion would have a plus charge, and that would dissociate. The carboxyl up above it, that hydrogen stays on the oxygen, like I said, depending on pH, and since we don't know anything about it, we're going to assume that it stays on there. Because of that, this deprotonated one, the COONA, is more polar than the COOH. And because of that, it's a slightly better choice, okay? So the key though is a non-polar end here on the left, that's hydrophobic. A polar end here on the right, that's hydrophilic. So for me, to be honest with you, if I was giving you a problem like this, I wouldn't have it this close with the Na and the H, because that gets into probably a little bit more than you really are expected to know in this class. But I would expect you to be able to say, is the one with CH3, CH211, and then the COOH, is that a better one than the CH3, CH2, CH2, COOH? Okay, hopefully that makes sense. We are out of time. I just want to remind everyone again that on Thursday of this week, we'll start chapter 14, and then we will have a quiz on chapter 13, okay? So any questions before we sign off? All right, thank you.